do first. All right, and now we switch to screen share. Get this set up. This take me just a second. It's the usual thing I go through every night. All right. Did anybody here take Latin? Let's see here. If you did, perhaps you know what that locus somniorum means that I've got that pops up on the screen there. Okay, so here we are. That locus somniorum is the name of a feature on the moon. Okay, so we finished up last Thursday night the nice felicitous situation which holds when you have a finite dimensional Hilbert space and you've got a Hermitian operator. So we're talking here about the spectral problem, which basically means eigenvalues and eigenvectors and so on. So the basic setup here is that you've got an operator A, an eigenvector U, and an eigenvalue lowercase a and vector U like this. So this is the eigenvectors here, the eigenvector, and the A here is the eigenvalue. I'll write it like that. Can you see that all right? Let's see, no, because there's a little yellow thing in the way. Let me pull it down a little bit. Okay, so we're talking about finite dimensions now, because it's good to cover that case first. We're talking about the case in which the operator is Hermitian, so A is equal to A dagger. And in those cases, there's a whole lot of simplifications in comparison to what happens with more general operators. In particular, the main points are that the eigenvalue is real. That means that the spectrum of the operator is spectrum is understood as being a subset of the complex plane. So the complex plane here is the eigenvalue plane, real part of A and imaginary part of A. But in any case, the spectrum consists of a discrete set of points on the real axis. That's the spectrum of the operator. So this is true of any Hermitian operator in finite dimensions. Kind of trivial concept, actually. Then there's various theorems, such as the fact that the various eigenspaces of the operator A are orthogonal to one another. Sometimes this is a statement sometimes it's stated in the following way. You say that if you have two eigenvectors corresponding to distinct eigenvalues, then they're orthogonal. But the geometrical meaning of that is related to the eigenspaces. In fact, the eigenspaces are an important concept because they give you I don't know if you saw that bug crawling on the screen there. They give you the operator A imposes a geometrical structure on the Hilbert space. It isn't easy for me to draw a vector spaces higher than 3 dimensions on a piece of paper. So let's suppose we have a 3-dimensional space. And let's suppose the operator A has 2 eigenvalues. Let me call them A1 and A2. And let's suppose the degeneracy is 2 and 1, like that. Suppose that's the case. Then the eigenspace for eigenvalue A1 is a 2-dimensional subspace. So I'll draw it like this. Let's call it E sub 1. In fact, let's use the notation E to stand for the whole Hilbert space. Yeah, was there a question? Did I hear a question? Okay, let's use a symbol script E to stand for the whole Hilbert space and E1 to stand for the eigenspace corresponding to eigenvalue A1, which is 2-dimensional, as I've indicated here, because degeneracy is 2. And the eigenspace corresponding to the second eigenvalue, which is E2, has a degeneracy 1, so it's a 1-dimensional space, and these spaces are orthogonal to one another. So in terms of the decomposition of 2 plus 1 equals 3, or maybe I should write it as, 2 plus 1 equals 3. This gives you an idea of the geometry of what's going on in Hilbert space. In case I didn't explain this last time, I'll write this notation E sub n here to be the nth eigenspace. And what the what an eigenspace is it's just the set of all possible eigenvectors of a given eigenvalue. In this case, we have a second eigenvalue A2. So this is a set of vectors contained in the Hilbert space such that A acting on U is equal to A2 multiplying U like this. And in this formula, we allow that U equals 0, the result being that the EN is a vector space. It's spanned by all these things. And so I've all these vectors that have the eigenvalue A2. So in this diagram, for example, the E2 is this two-dimensional plane, and then excuse me, E1 is the two-dimensional plane, and then E2 is a one-dimensional line like this. Any vector that I draw in E1, for example, is an eigenvector with eigenvalue A1. But since it's a two-dimensional space, there's lots of ways of drawing such vectors. To draw a basis in the space E1, I just choose an arbitrary orthonormal frame, two-dimensional frame in that space. Let's label the vectors by r equals 1 and r equals 2 like this. And if I do this and I call the vectors, let's say n and r like this, then these vectors are orthogonal for different values of r. And n and r prime scalar product gives me Kronecker delta r and r prime. For no deep reason. The only reason is because I chose an orthonormal frame in that space. But if I do that choice, I don't have to choose that. But if I do, I get this orthonormality relation. Now, on the other hand, an eigenvector that lies in a different space for a different value of n by the theorems that I discussed last time is automatically orthogonal to vectors in other spaces. So if I allow the n indices to be distinct, and I take an n prime r prime scalar product with n and r, doing a construction like this, you see in every eigenspace, then what you get is Kronecker delta n prime, Kronecker delta r prime, in which the n orthogonality is related to the theorem. Okay, so this is a way of illustrating the, as I say, the geometrical structure imposed on the Hilbert space by a Hermitian operator. And what it also leads to, as you can see, is an existence of a set of vectors that are orthonormal vectors in each of the eigenspaces. Now, the whole total collection of those vectors I can write as a collection of vectors n and r like this. Now, is this collection a basis of vectors on the whole space? And the answer is yes, it is, if the eigenspaces E1, E2, and others, if there's more, fill up the whole space. And in fact, that's exactly what does happen in finite dimensions. All Hermitian operators in finite dimensions are complete, and there's various ways of saying it. Last time I said they're complete if they possess an orthonormal basis of eigenvectors, eigenbasis in other words. But another way of saying it is that if the spaces, the eigenspaces E1 and E2, in a sense, fill up the whole space. So in regard to filling up the whole space, allow me to make a slight digression now onto the subject of the direct sum, which is a mathematical operation. It's indicated by a plus with a circle sign around it. And I'm not going to give the most abstract definition, but I'll give the one that is most useful in the present context. Let's suppose I've got two spaces, subspaces, let me call them A and B, like this. I'll use kind of script letters that are subspaces of the entire Hilbert space. Then what I mean by the direct sum of A plus B, to say it in words, this is just the set of all vectors you can make by making linear combinations of vectors from the two constituent spaces. So let's write it this way. It's a set of all vectors x plus y, such that x is in A and y is in B. That's a way of saying it. So as you can see, to go back to this diagram here, where I got this 2D and 1D space, if I take the direct sum of them, it gives me the 3D space, which in the context I'm describing here is the whole space. So what we've got then is a statement of completeness that can be stated in various ways. We can say that the operator A is complete if the direct sum of the eigenspaces E1 plus ... out to the last one, let's call it E sub n, is equal to the whole space E. And if that's so, by constructing orthonormal frame in each of the eigenspaces, then this set in R, where n and r run over all their allowed values, gives us an orthonormal frame of eigenvectors in the whole space. So if that's the case, then in R, the collection of all of these is an eigenbasis. It's actually an orthonormal eigenbasis. ON stands for orthonormal here. It's an eigenbasis. Okay. And that in turn, of course, means that an arbitrary vector can be expanded as a linear combination of eigenvectors, which is what we frequently want to do. Okay, so that's kind of a summary of the results in finite dimensions. I think in many cases, this would be proved by using these theorems about diagonalizing Hermitian matrices by means of unitary matrices, but this is the geometry, which I think is closer to how we'd like to think about it. Now, I mentioned that in a Hilbert space is an infinite dimensional space, which, however, that has a characteristic that many of its properties are the obvious generalizations of properties that hold in finite dimensions. This is fortunate because it means, as a practicing quantum mechanic, you can use finite dimensional intuition for an awful lot of what you need to do in real quantum mechanics, as we'll see. Go ahead with the course. But there are some things that are different. There are new features that are introduced in infinite dimensional spaces. And what I'd like to do now is to, by way of example, just go through some of the things that change. By the way, one of the things that does not change is the following fact, is that in a finite dimensional space, of course, all bases are discrete. They're labeled by 1, 2, 3 up to the dimension of the space. In an infinite dimensional space, that need not be true. You can have infinite dimensional spaces that do not have a discrete basis. That's to say, a basis is labeled by discrete indices. But in the case of a Hilbert space, it's always true that there exists a basis labeled by a discrete basis set. So it's in doing theoretical calculations in quantum mechanics, it's never wrong to assume a basis with a discrete set of indices. Now, this is in spite of the fact that in practice, as we'll see later on in this lecture, in many cases, we use so-called bases, quote unquote, which have continuous indices. Just because we do that doesn't mean that bases with discrete indices don't exist. They do exist, they always exist for a Hilbert space. So that's an example of how the properties of finite dimensions get carried over in the obvious way to infinite dimensions. All right, in any case, let me move on then to talk about the infinite dimensional case and how some things change for that. So let's get my papers arranged here. So let's move on now to infinite dimensions. So I'm just going to run through some examples to show you what the possibilities are. Let's start off with a harmonic oscillator Hamiltonian and wave mechanics in one dimension. So you have the usual Hamiltonian for a harmonic oscillator, p squared over 2m plus m omega squared x squared over 2. And you know that this possesses a discrete set of energy eigenfunctions un of x, which are normalizable, and where n goes from 0, 1, 2, 3, all the way out to infinity. We could write these in Ket language as simply n like this. They're orthonormal, so that n m scalar product is Kronecker delta n and m, like that. And they're complete, which is can be represented by a resolution of the identity that says that 1 is a sum on n of n outer product with itself, n equals 0 to infinity. It's an infinite sum of the resolution. In finite dimensions, this would be a finite sum, but the sum is just extended to infinity, and that works in this case. So what the harmonic oscillator shows is that the Hilbert space, in this case, the space of normalizable wave functions in one dimensions, does indeed possess a basis with a discrete, labeled by a discrete index. And this is it. There's one example of it anyway. These basis vectors are normalizable, and they are therefore can be made and they're also orthogonal to one another, so that the basis constructed out of them is an orthonormal basis. Let's see. So this is an example of what's called the discrete spectrum. And the discrete spectrum, as this example shows, sometimes occurs in infinite dimensions. In finite dimensions, you always have a discrete spectrum. There's no alternative because you just get this collection of points here in the real axis for the spectrum. For the case of the harmonic oscillator, of course, the energy eigenvalues are n plus a half, as you know, times h bar omega. That means if we look at the spectrum of the harmonic oscillator, you need to look at this in the complex energy plane with real energy and imaginary energy. There's an eigenvalue at 1/2. There's another one at 3/2, another one at 5/2, 7/2, and so on. And all of this is the spectrum. This is the discrete set, which is the spectrum of the harmonic oscillator Hamiltonian. I think mainly what I'm doing here is just explaining terminology for some facts that you know already, but this is how it works out. Now then, let's see. So in this case, the eigenvalues are non-degenerate, meaning that all the eigenspaces are one-dimensional. And we can say that the total Hilbert space E is the direct sum of E0 plus E1 plus going all the way on out to E infinity. It's an infinite direct sum of eigenspaces corresponding to the different eigenvalues. All right, now let's take a different example. Let's talk about the momentum operator, another example of a Hermitian operator in infinite dimensions. Let me get this here, get this centered here. So let's begin by looking at the eigenket eigenvalue problem for the momentum operator. Let's use a hat to indicate the operator so that p hat, let me write it over here. P hat is equal to the momentum operator. And let's use P without the hat to be the momentum eigenvalue. Then the eigenket eigenvalue problem looks like this, is that P hat acting on P is equal to P multiplying P. To be clear about the notation, I just explained that P hat is the operator and P is the eigenvalue. The eigenket is denoted by a ket with a P symbol stuck in it. That just means that it's the eigenket, or sometimes we'll call it a state. It's the eigenket, which has an eigenvalue given by P. By the way, these two types of notations, P, one the operator and one the eigenvalue, are given names by Dirac. Dirac gave terminology for this. The ordinary number is what Dirac calls a C number, whereas the operator is what he calls a Q number. And this is convenient notation, which we'll hear a lot in this course, is due to Dirac. And I think the C and the Q for Dirac were mnemonics for classical and quantum. But when I talk about a C number, I'm really just trying to emphasize that the object that I'm talking about is usually either an eigenvalue or perhaps also, or alternatively, a classical quantity in some kind of a classical model, which of course is an ordinary number and not an operator. So that's the contrast which is to be drawn. But in any case, the P here without the hat is the C number and the P hat is the Q number. This notation of writing the eigenket by labeling it by the eigenvalue is extremely common in quantum mechanics. It's used everywhere. Everybody uses it all the time and will do so also in this course. But there's a tiny danger that's lurking in it. And if you're a careful person, you'll pay attention to this, which is that an eigenket, or an eigenfunction, if you will, is not uniquely determined by the eigenvalues, assuming that it is an eigenfunction of some operator. It's not uniquely determined by the eigenvalue. And the reason is because there's an arbitrary phase that's in there. There's an arbitrary phase if it's one-dimensional. If it's multidimensional, like we saw in that diagram on the last page I was drawing, then there's actually a two-dimensional frame you can choose in the eigenspace. But even in the non-degenerate case, there's a question of a phase convention. And many people in physics, it's almost a tradition is just to blow off phase conventions to assume they don't matter, but in fact they do, and they're quite important in a number of applications, such as well, people miss some important things in Born-Oppenheimer theory, for example, for decades because they weren't paying attention to phases. All right. In any case, that's just a little warning there. So anyway, if I take this equation here and I translate it into wave function language, the momentum operator is minus I h bar d dx, like that. It's corresponding to the p hat here. And then the p ket, let me write this as a wave function language, as u sub p of x. That means an eigenfunction of the momentum operator with eigenvalue c number, you see lowercase p. And that's equal to the eigenvalue multiplying u sub p of x. Now this simple differential equation has a solution which is given by u sub p of x is equal to some normalization constant times e to the I px over h bar, like so. And this is actually valid for any value of the momentum eigenvalue p, whether real or complex. So this is any p in the complex numbers, like that. Now then, does that mean that the spectrum of the momentum operator consists of the entire complex plane? And the answer is that no, I can't explain it in detail without going further into the functional analysis than I wish to do, but I can tell you what the custom is, well-justified custom. And it runs something like this. In the case, if we go back to the harmonic oscillator, we know that the eigenvalue n, or quantum number n, is not arbitrary, but rather it's chosen in order to make the wave function normalizable. So let's ask about normalizing. That's what determined the vectors in Hilbert space and the allowable eigenfunctions. What about the momentum operator? Let's look at the normalizability of these wave functions. In the first place, if the momentum p has an imaginary part, either either positive or negative, then this wave function diverges exponentially as x goes to infinity or as x goes to minus infinity. And so it's really quite badly behaved and certainly is not normalizable. On the other hand, if the momentum is purely real, then we don't have the exponential divergence, but we do have a wave function which is still not normalizable because it just oscillates forever going out to x plus and minus infinity, and its norm is infinite. So if you're looking for an eigenfunction of the momentum operator defined in this way, which by the way is a Hermitian operator, if you're looking for an eigenfunction which belongs to Hilbert space, Hilbert space eigenfunctions, the fact is the momentum operator simply doesn't have any, has none whatsoever, much less an eigenbasis of such things. Doesn't even have a single eigenfunction, period. On the other hand, if we look at the case where the momentum is real, and remember in finite dimensions for a Hermitian operator, the eigenvalues are real. If we look at these in the case where the momentum is real, it turns out that the wave functions or the states have some properties that are generalizations of what we saw in finite dimensions. So in particular, let's choose the normalization constant to be 1 over the square root of 2 pi h bar, because if we do that, and then we compute the scalar product of eigenfunctions of different eigenvalues, let's say p and p prime scalar product. Recall that in finite dimensions, this would be a Kronecker delta in the eigenvalues. What is it in this case? Well, this is to work out, this is an integral. You just do the integral. It's integral dx. I'm going to have u sub p of x complex conjugated times u sub p prime of x. And if you do the integral, you get a direct delta function in p minus p prime. So these quote unquote eigenfunctions are not normalizable in the usual sense, but they do have an orthonormality relation in the sense of a Kronecker delta, which in the sense of a Dirac delta function rather than a Kronecker delta, which of course is logical given that the eigenvalues are continuous. All right, so they have a kind of a continuum orthonormality condition. What about completeness? Are they complete? Well, they would be complete if we could take an arbitrary wave function psi of x and write it as a linear combination of these up of x's. Now, given the fact that the p is a continuous variable, this linear combination can't be a discrete sum, but rather has to be an integral. So let's put some coefficients in here. I'll call phi of p, and then put an integral in here, integral over dp. And the question is, can we do this? As to say, for a given psi, is there coefficients phi of p that makes this equation true? And the answer is yes, because if I just plug in the formula for the u of p, this turns into an integral over p over root 2 pi h bar of e to the I px over h bar times phi of p, looking at it like that. And the result is we see that phi of x is the Fourier transform modulo factors of h bar and so on. It's a Fourier transform of phi of p, which means that phi of p is the inverse Fourier transform, integral dx over the square root of 2 pi h bar of a psi of x times e to the minus I px over h bar. So in other words, there does exist, using the theory of Fourier transforms, there does exist coefficients for a quote unquote arbitrary function psi of x. Actually, we're only interested in normalizable functions. If you want to talk about a Hilbert space, that means the corresponding phi of p's are normalizable as well by the Parsifal identity. In any case, what we see then is that these wave functions, these quote unquote eigenfunctions, which don't belong to Hilbert space, where are they here? Right here is the formula for them, that they are complete in this sense. Let's take this completeness relation. Was there a beginning of a question? Did I hear?
Yeah. I was so does this notion of like a Fourier transform between x and p, is this like similar to this like notion of like the dual between like Bras and Ketz? Like, is there?
No,
Okay.
no. This is not. No, the dual between Bras and Ketz is forming a mapping. What I call the dual correspondence is forming a mapping from a ket to a bra, which is a linear, a real value linear, complex value linear functional on Ketz. That's what that was. This is transforming actually, what we're doing is we're transforming, as you well know, is transforming position space wave functions into momentum space wave functions. But the angle that I'm giving it on here at this point is to demonstrate that the momentum space eigenfunctions created in this way, so-called eigenfunctions because they don't belong to Hilbert space and therefore don't represent physical states, they nevertheless do form a basis in a certain sense, because I can write an arbitrary wave function as a linear combination of them.
Okay, gotcha. Thanks.
All right. So anyway, that's just using the Fourier, the properties of the Fourier transform. Now, allow me to take this formula for phi sub p, which I just wrote down here, and write it in a slightly different form. Let me write it as integral of dx. And let me write it as u sub p of x complex conjugated times psi of x. And if I write it in that form, then you can see that in Bra-Ket language, this is a scalar product of p with psi, like so. Let me keep that for a moment and bring down here. Likewise, if I take this function, this expression up here, which is expressing psi as a linear combination of the use of p's, and I write that in Ket language, let me just write Ket psi to stand for this wave function psi of x. This is the integral over p, and I'll write the up of x next. That's in Ket language. It's just this state p like that, and then the coefficients phi of p I'll put in like that. Okay. However, I just showed that phi of p is the scalar product p psi. So this is also the integral dp of Ket p like this, scalar product p psi. So now what we've got is an arbitrary vector like this is represented by an integral like that. Well, the integral like that, allow me to write it this way, is integral dp of p outer product with itself acting on psi, which I can do by the definition of the outer product. And I think what I'm going to do is to turn on my light and try to get a better lighting on this page, which I think will help it make it more easy to see it. Let me also relock the screen, which I think helps it a little bit. I hope that's better. Looks better to me. All right, in any case, this is true for arbitrary vector psi, and therefore it implies that the integral dp of p outer product p is equal to 1. And this is therefore as a resolution of the identity, indicating a completeness relation, which corresponds to what we saw in finite dimensions, where you had the sum on n of n outer product n is equal to 1. Actually, not just in finite dimensions, but also in the case of the discrete spectrum in quantum mechanics. So in the case of the continuous spectrum, we do have a kind of an orthonormality and completeness relation, but the eigenvectors don't belong to Hilbert space. The orthonormality condition is expressed in terms of Dirac delta functions rather than Kronecker delta functions. The eigenfunctions are not normalizable, which is I just mentioned a minute ago. And we also have a completeness relation as well, but it involves an integral like this of the outer product of these sort of pseudo eigenfunctions like that. All right. So these are the main features then, as illustrated by the momentum operator of what's called the continuous spectrum. And by the way, in this case, the spectrum of the momentum operator would look like this. We take the real and imaginary parts of the momentum eigenvalue, and the spectrum of the momentum operator is considered to be the entire real axis like this. So this is why it's called a continuous spectrum. It's not a set of discrete points. And that's one of the possibilities that happens in infinite dimensions. Now, here's another possibility that can happen in infinite dimensions. Allow me to take a potential energy V of x, which looks like this. The potential comes in, it's mostly 0, and then it goes into a well like this, and the well goes down, and then when the well comes up, it rises up this way and goes to infinity to create an impenetrable barrier. So this is a problem in 1D quantum mechanics. In general, there are bound states in the well. There's one that looks like a Gaussian sitting here in the bottom of it, and then there's a first excited state that looks like that, and so on. There may be other discrete levels in here. Let's call these levels E sub n here, like this. And these are all have negative energy. The bound states have negative energy. On the other hand, if we send in a particle of positive energy, it's a scattering problem. The wave comes in like this, hits the impenetrable barrier and bounces back. And so what we get is a sum of two waves, an incident wave and a reflected wave. And these are energy eigenfunctions for energy positive. In fact, there's such eigenfunctions for all energies greater than or equal to 0. So in this case, we have what's called a mixed spectrum. That is to say, there are discrete normalizable energy eigenfunctions corresponding to the bound states. But there's also a continuum of states in the continuum like this, which are characterized by positive energies. So in this case, the bound states can be normalized in the usual discrete sense. That is to say, the Kronecker delta normalization. That means any individual state is normalized and it's orthonormal with the other discrete states. As far as the states that are in the continuum is concerned, let's just write these as E like this, being labeled them by their energy eigenvalue E. They're non-degenerate in the way that I've drawn this here. If we normalize them properly, you can't normalize them in the sense of making their norm equal to 1 because they're unnormalizable in that sense. But if we multiply them through by an appropriate normalization constant, we can make them normalized in the delta function sense to make them give this relation here, that their scalar product is a Kronecker, is a Dirac delta function in the energy. Then the resolution of the identity looks like this. The identity is given by the sum over the discrete states, outer product n like this, plus an integral from 0 to infinity over energy dE. And then we have the outer product of E outer product like so. And this is the resolution of the identity in this case, which is an example of what's called the mixed spectrum. And in this case, you can imagine what the spectrum looks like. If I sketch the spectrum, it's going to be a subset of the complex energy plane, real energy and imaginary energy. And it looks like this. Your bound states are down here at negative energy like so. They're discrete. But for positive energies, you've got a continuous spectrum that goes out like that. It goes out to infinity. So this is the spectrum of a problem of that sort.
Professor, what would the inner product of a discrete and a continuous eigenvector look like in this
Thank you.
example?
I forgot to mention that. Those are orthogonal to one another. And you see, it's just a simple generalization of what you have in finite dimensions, which is that eigenstates corresponding to distinct eigenvalues are orthogonal, and that holds here too. All the bound states are orthogonal to all the scattering states. Okay. One of the there's other more complicated types of spectra as well. There's possibility of discrete states embedded in the continuum, which we'll see later on in the course. We'll see examples of that. However, let me just mention that these three examples I've given you here, the harmonic oscillator, the momentum, and this potential problem, we're all non-degenerate. In reality, that you frequently have degeneracies. Let me just mention the case of the hydrogen atom. If you look at the hydrogen atom, you have let's begin by drawing the spectrum. Again, we've got the real energy and imaginary energy. There are bound states that have negative energy here. Let's say this is the ground state E1 like that. That's of course minus 13.6 electron volts. Then you have other bound states up here, and there's actually an infinite number of them, and they accumulate. The infinite number accumulated up to E equals 0. What happens above E equals 0 is you have a continuous spectrum of unbound states going out like that. And this is the spectral diagram for the hydrogen atom. You see, it's not so different from that diagram I drew for the 1D potential model. Anyway, this is what it is. The bound states are indicated by quantum numbers n, l, and m. This is usual notation in the hydrogen atom. And they're orthonormal in the sense that if I form their scalar products with different sets of quantum numbers, these are all discrete quantum numbers for the bound states, you see, you get a product of 3 Kronecker deltas. If you like, the energy is determined by n only. So the orthogonality for different values of n is related to this theorem about distinct eigenvalues. As far as the others are concerned, the L prime and M prime, this has to do with the fact that these are also eigenstates of further operators. And again, distinct eigenvalues corresponds to orthogonality. Now then, on the other hand, there are continuum states too for positive energies, for energies or non-negative energies. For non-negative energies, we can write these as E and ELM. They're eigenstates of the energy in the Hamiltonian, the energy that is, as well as L squared and LZ. So this is a notation for them. And what is their orthonormality relation? It looks like this, ENLM. Sorry, do it right. Here, let's do it right. It's ELM, scalar product with E prime, L prime, M prime, is a Dirac delta function in E minus E prime, Kronecker delta in L and L prime, and a Kronecker delta in M and M prime. Kronecker deltas you see in the discrete indices, and a Dirac delta function in the continuous indices. And by the way, you won't get this Dirac delta function unless you scale the eigenfunctions appropriately, like we did for the momentum eigenfunctions. We had to choose that constant C to get this to come out right. But you can always do it, and you end up with this sort of standard form for orthogonality. So here's the orthonormality for the discrete states. Here's the orthonormality for the continuum states. And continuing with that question I was just asked a minute ago, if you take the scalar product of a bound state with a continuum state, looks like this. Those are orthogonal. All bound states are orthogonal to all scattering states. So that's how it works out for hydrogen. And by the way, in the case of hydrogen, a resolution of the identity looks like this. It's a sum on NLM of the outer product of NLM with NLM, plus an integral from 0 to infinity, energy dE, a sum on L and M of the outer product of ELM with ELM. If you ever do any work with a hydrogen atom, it's important to remember that the bound states alone don't form a complete set. You've got to include the continuum as well, and it's oftentimes quite important in practice. All right, so those are examples, a bunch of examples, 4 of them, of different types of spectra and infinite dimensions, and showing you what happens when you have a continuous spectrum.
Professor?
Yeah, a question.
Yeah, what determines the lower bound of this integral? Like, is it always going to be from 0 to infinity when you're
well, in kinetic plus potential problems of this form, the continuum, what you call a continuum threshold, that's where the discrete states turn into the continuum, happens at E equals 0. And that's really a convention of the usual convention for potential energies. The Coulomb potential energy vanishes at infinity. That's really the reason for it. If positive energies correspond to an electron which is unbound, so it's able to travel all the way out to infinity. Does that help?
Yeah, I think
in a different problem.
It's just convention.
Yeah, it's related to the conventions for the potential energy. In fact, in different problems, the continuum threshold could occur at a different place. Not all problems have a continuum threshold. The harmonic oscillator doesn't. It has discrete levels going all the way out. On the other hand, it's got this parabolic potential energy that goes to infinity, which is, right. In real applications is really unrealistic.
Yep, got it. Thanks.
Okay. Now then, let's see. Here's another point I'd like to make. In the case of the discrete eigenvalues and therefore normalizable eigenfunctions, we were able to talk about the eigenspaces, which I called E sub n, the eigenspace. So this is something that corresponds to an eigenvalue. Let me call it A sub n in a general notation of A sub n as a discrete eigenvalue of an operator capital A, let's say. And as I explained, the dimensionality of that space is the order of the degeneracy, that is to say, what we call well, I call it the order of the degeneracy. Say twofold degenerate means two-dimensional. What about the continuous spectrum? For example, suppose we're talking about the momentum, and we pick a particular value of momentum eigenvalue, say p equals p naught, let's say, one value. The question is there a subspace of the Hilbert space corresponding to the eigenvalue p naught? There certainly is a wave function. It's e to the I p naught x over h bar. But that wave function is not normalizable and therefore does not belong to Hilbert space. The result of this is that in the continuous spectrum, there is no subspace of the Hilbert space corresponding to a single eigenvalue. Instead, what you find is that there are subspaces corresponding to intervals of a continuous eigenvalue. I'll illustrate this for the momentum. Let's suppose I have an interval in the momentum axis. I'll call it I, and it goes from P0 to P1 like this. Then I can define a subspace of the Hilbert space. I'll call it E sub I, and here's what it is. It's a set of wave functions psi of x such that the Fourier transform phi of p is equal to 0 outside the interval I. And of course, you also want psi scalar product to be less than infinity. You want to be normalizable wave functions. So this is what we mean by the subspace. It clearly belongs to, it's a subspace of Hilbert space because it consists of Hilbert space functions. But what this would mean is if I plot the momentum space wave function here, here's P and here's phi of P, and I've got the interval P0 here and P1 here, then the momentum space wave functions are ones that are strictly 0 outside this interval. So inside this interval, they can do anything they want, like this, but outside they're strictly 0. So this is the phi of P. So this gives us a set of wave functions which are normalizable. They're a subset of these, actually a vector subspace of the Hilbert space, and this is the E sub I. So in the continuous spectrum then, to summarize, we have subspaces of the Hilbert space corresponding to intervals of the continuous variable. Now then, allow me now to move on to, so all I've been doing here is just giving you examples of what happens in infinite dimensions. If you do a course in functional analysis, the right course, they'll go through all this in rigorous detail, and they'll end up proving a massive theorem that's central to the whole course, sometimes called a spectral theorem. And I'm going to give you a physicist version of that theorem right now. And the theorem is the following: is that a complete Hermitian operator has an orthonormal eigenbasis, ON, which stands for orthonormal eigenbasis. Now, in making this statement, it's necessary to understand that in some cases the spectrum is continuous, and that means that the so-called basis vectors actually don't belong to Hilbert space, but they still form a basis in the sense that I've been describing up above. Actually, the mathematicians don't like to talk about those basis vectors. Instead, they want to talk about the projection operators, and if you read the literature, you'll see how they do that. But in any case, this is how we want to apply it in quantum mechanics. This is basically a theorem that says that in the case of a complete Hermitian operator, it's never wrong to assume that there's an orthonormal eigenbasis. This is something we do all the time, as I think you're familiar with, and I'm just stating this as a formal property here.
So can we also do a direct sum of all the interval subspaces, and that would span the space?
No, because there's as many intervals as there are pairs of P's. So you see that some of them would overlap, and that wouldn't work.
So it's every single possible combination of P.
Oh, I see what you're saying. So, I mean, are you saying suppose we take the allowed, well, for the real momentum, for example, goes from minus infinity to plus infinity, and you're saying suppose we broke this up into, let's say finite chunks. There's an infinite number of them, and then we took the direct sum of all the projectors. Would that be the whole thing?
Yeah, can you do that? Can you choose?
The answer is very much so. In fact, what you say is exactly right. In fact, let me go back here because, well, I haven't been talking about projectors yet. Let me wait a minute until I come back to until I do projectors, and I'll come back to that point. You'll see exactly how that works. But no, what you're saying is exactly right. I mean, clearly, if it was clearly, I could take any momentum space wave function and break it up into a sum of terms that that were non-zero and on just one of each of the intervals and add them up, and I'd get the whole thing. You can do that. So I think that's the intuition of this. All right. So allow me to write this theorem down in some kind of a general notation. Let's suppose I've got A as an operator. It's a complete Hermitian operator. By the way, let me make a slight digression here. In finite dimensions, as I mentioned, all Hermitian operators are complete. This isn't necessarily true in infinite dimensions. There exist Hermitian operators that are not complete. In fact, to do it right, you need to distinguish between Hermitian and self-adjoint. And if you get into the mathematical literature, you'll need to worry about that. In a course like this, we don't worry about that very much, and we just sloppily speak of Hermitian operators. And as a matter of fact, we will in this course, and the literature does this almost all the time. One normally assumes that all Hermitian operators that you encounter actually are complete. But in fact, there are, I think, sort of pathological cases, you look at them that way from the standpoint of physics, of Hermitian operators in infinite dimensions, which are not complete. And so for that reason, we invent a definition, which I'll give you here now, is what we call an observable. An observable is a complete Hermitian operator. And what we will do in this course is, without comment, we will assume that all the Hermitian operators that we encounter actually are observables and are therefore complete. In any case, if we have a complete Hermitian operator, i.e. an observable, then it possesses an orthonormal eigenbasis. This is almost proven by, or demonstrated anyway, by the examples I've been through. But let me just develop a notation for writing this down. Let's suppose that A is our operator. Let's suppose it's got a discrete spectrum I'll indicate with a discrete index n with eigenvalues a sub n in R like this. And the R is an index which is used to resolve the degeneracies. It may also have a continuous spectrum, which I'll indicate by nu R, where nu is a continuous variable. And this is given by an eigenvalue a, which is a continuous function of nu R like this. The nu here is just a continuous variable that's used to label the eigenvectors, and the eigenvalue is a function of nu. The eigenvalue itself is also continuous, and if you wanted to, you could label the eigenvectors by a instead of by nu. That's just what we did with energy in these various problems I was just referring to. But there are other cases where you want to use a different parameter. So, for example, you might want to label an energy eigenvalue by the momentum parameter of that, that corresponds to the given energy. So that's what this notation allows us to do. And besides, the nu sort of looks like an n, and it's kind of an obvious continuous generalization of that. In any case, if this is a combination of a mixed spectrum of some operator A, then the resolution of the identity looks like this. It's a sum on n and r of the outer product nr. Oh, let's see. Before I do that, I should before I write down the resolution identity, I should write down the orthonormality relations. Let me do that first. It's nr scalar product with n prime r prime is Kronecker delta nn prime, Kronecker delta rr prime. Nr scalar product with nu r prime is equal to 0, and nu r scalar product with nu r prime is given by Dirac delta function in the nus times a Kronecker delta in the r's, like so. And if we have these orthonormality relations, then the resolution of the identity is the first discrete term that I've given here, plus an integral over d nu, and then the sum over index r, and then nu r outer product. Okay, like that. By the way, when I use this index r here to, as I say, resolve degeneracies, that means to specify a set of vectors inside the degenerate eigenspace that form a basis in that space. The notation I've been using indicates that the r is discrete. Well, the eigenspace, let's speak of the discrete level here. The eigenspace, therefore, is a real vector subspace. The eigenspace is a subspace of a Hilbert space, and therefore it's a Hilbert space in its own right, and therefore there exists a discrete basis in it. So there's nothing wrong with using a discrete index like this for this R. However, in practice, you may find that you want to use continuous indices inside an eigenspace of a larger space. That sometimes happens. For example, we'll see this when we come to the Landau problem. The particle will charge the problem of the motion of a charged particle in a magnetic field. We'll deal with that in a few lectures down the line. That's where that occurs. All right. In any case, the R index, in some cases, you might want to make it continuous, but for discrete notation, this is what we have, and this is the resolution of the identity. So the content of the theorem here is this observable possesses as an orthonormal eigenbasis is contained in this boxed equation right here. All right. So that's kind of a big theorem, which I don't prove, but I just illustrate by some examples. Let me discuss some other theorems that are related to this now important result on the existence of orthonormal eigenbases for operators with all these understandings that go into it, including infinite dimensions and continuous spectra. Here's an important theorem which arises in many cases. Let's let A and B be two observables. Then the theorem says that A and B possess, write it out, they possess a simultaneous eigenbasis if and only if they commute. Now, a simultaneous eigenbasis is important in many applications. It just means that you've got a basis set of basis vectors, each of which is an eigenvector of both operators A and B. And this theorem is saying that such a basis exists if and only if the two operators commute. I'm going to prove this theorem, at least in finite dimensions or for a discrete spectrum, because that will convey the main idea. So let me, or at least I'll give a partial proof on it. Let's work on a partial proof of it. This is an if and only if, so it goes both directions. Let's assume that A and B commute. All right. And let's for simplicity, let's work in finite dimensions so that I don't have to worry about the continuous spectrum. So then A then has a eigenvalues I'll call lowercase a sub n, like this. And corresponding to a sub n are eigenspaces I'll call En, which may be multidimensional, like so. Let's focus on some value of n, and let's sketch the eigenspace En like this of the operator A. Now then, before I proceed, I want to make a digression into the concept of a what you call an invariant subspace. So this is a digression now. So let's let S be any subspace of our Hilbert space, and let's let X be an operator. Then we have a definition. We say S is invariant under X if, to say it in words, it's invariant under X if X maps any vector in the subspace S into another vector which also belongs to S. So we'll say it this way: if psi belongs to S, implies that X psi belongs to S. In other words, if you restrict the domain of the operator X to not be the whole Hilbert space, but just the subspace, then the image of the operator X belongs to the same subspace. If that's the case, you can speak of the restriction. This leads to the concept of the restriction of the operator X. The restriction of operator X to the subspace S is nothing but just taking the same operator without changing it at all, but just restricting its domain. That's to say, the set of vectors it's allowed to act on. And you just make that into S itself, and then you have, as I say, all the outputs are also lie in S as well. All right, so this is a digression here to make a definition of this notion of an invariant subspace. Let's go back now to our operators A and B, which commute, and here's the eigenspace of A, which I called En. It has a 0 point, so I'll put that in right there. This space En is actually invariant under the operator A. this just really follows from the definition of an eigenspace, because in an eigenspace, every vector in the eigenspace is mapped into itself by the operator A. So naturally, it's invariant. In fact, it's more than that. The operator A restricted to the subspace En is really just a constant. It's just a multiplication by An. That's all it is. Allow me to use an overbar to indicate the restriction of A to the subspace En. Then the A bar is just equal to An times identity on that space. All vectors just get multiplied by An. Now, let me skip over the digression here and come down below to make some space here like this. Can you see this? Let's come down here. It turns out the subspace En is also invariant under B. How do we know this? Let's take A, let's do it this way. Let's let psi belong to En. That means that A psi is equal to lowercase a times psi, or An times psi. Now let's multiply both sides by B. So BA psi is equal to A sub n is a C number, so it commutes with the operator B, so I can write this as A sub n times B psi. On the other, the left-hand side is also equal to AB times psi, because we're assuming that A and B commute. That's part of the theorem. So let's take this final result, and let me just write it in a different form to just emphasize what's going on. A acting on B psi, that's this thing here, is equal to A sub n multiplying B psi. And that means the vector B psi is an eigenvector of A with eigenvalue A sub n. And that means that B psi then belongs to the subspace En. And so what we see is that if psi belongs to En, then B psi also belongs to En. So therefore, as I said earlier, this space En is invariant under B as well as under A. Now the operator B restricted to En is not a constant like A was, because this is not an eigenspace of B. The operator B was a Hermitian operator in the large Hilbert space. And so if I restrict it, and we call it B bar, if I take the B bar as the restriction of B to the subspace En, it's still a Hermitian operator in that space. And and therefore a Hermitian operator in Hilbert space by our grand theorem possesses an orthonormal eigenbasis. So that means we can choose an orthonormal eigenbasis inside En, let's say is indexed by, let's say some R value like this, R equals 1, R equals 2, such that B bar acting on these vectors, let me call them NR, brings out an eigenvalue, let's call it BR, NR, like this. Can you see that up there? I think I've got a shadow here. Let me get the shadow out of the way. So in other words, the B possesses an eigenbasis inside En, and that is therefore is a simultaneous eigenbasis of both A and B inside En. But now we do this for all the other eigenspaces of the operator A, and you get overall a basis in the entire Hilbert space that's a simultaneous eigenbasis. So this is a slightly geometrical proof of that theorem going one direction, proving that if the observables commute, then they possess a simultaneous eigenbasis. The converse I won't prove in lecture because it'd take too long, but it's contained in the notes in case you want to look it up, or you can try it for yourself just for practice. All right, so that's an important theorem. Here's another theorem that's important and actually arises in a surprisingly large number of cases. Theorem is this. Again, let's make A and B are observables. So let's let these be observables. Like that. And then the theorem is the following, is that let psi be a non-degenerate eigenstate of A. Oh, and we're going to assume that A and B commute. So A and B are two observables that commute. Let psi be a non-degenerate eigenstate of A. Then psi is an eigenstate of B. It's automatically an eigenstate of B. How do I prove this? Part of the proof is very similar to the proof of the last theorem. It works like this. A is an eigenstate of A, so we have something like this. A psi is equal to A n psi, like so. Now, what about B? Let's apply BA acting on psi. That's equal to AN times B psi. However, this A psi, we said this was non-degenerate. That was part of the theorem. So BA psi is equal to A and B psi, but that's the same thing as AB psi because A and B commute. And so what we get is A acting on B psi is equal to A sub n acting on B psi. This is exactly what I did a minute ago, and it just shows that B psi belongs to the eigenspace of A with eigenvalue A sub n. However, in this case, that eigenspace is one-dimensional because we're assuming that this is non-degenerate. And in a one-dimensional space, all vectors are proportional to any non-zero vector. The psi here is certainly non-zero because it's an eigenvector, and we understand eigenvectors to be non-zero. Therefore, it follows that B psi must be with some proportionality factor proportional to psi. Let's call it proportionality factor lowercase b, and thus you see that's an eigenvalue. And this then proves the theorem is that psi is also an eigenstate of B. Now, this looks like a fairly specialized theorem, and in fact it is, but it gets used, I think we'll probably use it at least 5 times this semester coming up. So pay attention to it. You'll see it arise again. All right, so those are some theorems then about the spectral theorem of linear algebra of Hilbert spaces and applications in quantum mechanics. I have one more brief article, a topic I want to cover before I get out of this mathematical stuff, and that's to say I want to talk about projection operators. Let me begin with a definition. A projection operator, which is also called a projector, is an observable, first of all, complete remission operator. It's such that ST means such that P squared is, let's say observable, projection operator, let's call it P as for give it a name. It's an observable such that P squared is equal to P. I see that I've been using the wrong pen here, and nobody's complained. I try to use this pen with a larger point so that I write bigger. So that's the definition of a projection operator. This property P squared equals P is called idempotent. That's to say, operator that satisfies this is called idempotent. This comes from Latin idem, which means the same, and potent, which means powerful. So the second power is the same as the first power, and that's where the phrase comes from. All right. Now, why does this definition give rise to what we think of as a projection operator? The reason is the following. Let's look at the eigenvalue eigenket problem for the projection operator. Let's have capital P acts on lowercase p, brings out lowercase p, multiplying lowercase p. Now, I'm sorry about the notation a minute ago. This was a momentum eigenstate, but now I want this to be an eigenstate of the projection operator that both have p's in them. So this is an eigenstate of the projection operator with eigenvalue lowercase p. If I take the operator p squared minus p, which by the definition of a projection operator, that's actually equal to 0. And I apply it to the eigenstate p like this, what I get is lowercase p squared minus lowercase p multiplying lowercase p eigenstate is equal to 0. But the eigenvector is non-zero, so the coefficient has to be 0. P squared minus p is equal to 0. And this implies that p is either equal to 0 or 1. And thus the eigenvalues of a projection operator defined by this definition are only 2. They're 0 and 1. And since it's an observable, it means that the Hilbert space then breaks up into 2 orthogonal subspaces, which I can't sketch very well in infinite dimensions. So let me do the best I can, like this. Let's call this space E1, and let's call this space E0. E0 is the subspace in which vectors get annihilated by P because the eigenvalue is 0. So if it multiplies by 0, it kills them. Well, look at what a vector is in this space. It's sticking up like that. It's like if you're standing out in the sun and the sun is straight overhead, the shadow is well, there's no shadow at all. It disappears. So the projection coming down from above just destroys the vector if it belongs to E0. On the other hand, if you're lying flat on the ground, as to say inside E1, then the projection, the shadow, is the same thing as yourself. It's an image of yourself. And if you apply it twice, it doesn't do anything more. It stays the same. So this is why this is a subspace E1. Multiplying by 1 doesn't change the vector. The general vector, of course, is a linear combination from these two subspaces. And if you project that, then you get the E1 part. It punches out the E0 part. So this is the geometry then of projection operators in terms of geometry in Hilbert space. Well, and so you see a projection operator has an eigenspace with eigenvalue 1, which is the subspace upon which the projection operator projects. And the complementary space, the orthogonal space, is annihilated. These are frequently something that's oftentimes infinite dimensional. Now, what about our subspaces E sub n for the eigenspaces of a Hermitian operator with a discrete eigenvalue? What about those? Well, there should be a projection operator Pn corresponding to that. And in fact, it's easy to see what it is. It's given by a sum on R of NR outer product NR, like so, like that. This is the operator which reproduces any vector inside that space, but annihilates any vector orthogonal to that space. In the case of the discrete spectrum, either finite or infinite dimensional, we had the fact that the total Hilbert space was the direct sum of the eigenspaces corresponding to the various eigenvalues going on out like that. Well, there's an equivalent statement that can be expressed in terms of projection operators. It is that the identity is equal to the sum on n of the projection operators Pn, like this. This applies in the discrete spectrum. It certainly applies in finite dimensions, and it also applies in the discrete spectrum in infinite dimensions. So these are called complementary projectors because they project onto orthogonal spaces and the sum of them adds up to 1. This is another expression of a resolution of the identity, or if you like, a completeness property for the original operator with a discrete spectrum. What about the continuous spectrum where we had these intervals? What about an interval I, which, let's take momentum, for example. We had P0, P1, like so. And I explained that there was a subspace E sub I corresponding to that. I explained what the subspace is. What is the corresponding projector Pi? Well, Pi is this. It's given by an integral over the interval P0 to P1 dP of the outer product PP, like so. And this then gets to the question which a student raised a few minutes ago. You can see that if you allow the interval, the limits of the integral, P0 and P1, to extend to plus and minus infinity, then you get the resolution of the identity and Pi just becomes 1. But if it's only over a finite interval, then this is not 1, it's a projector onto that subspace. So this is how projectors are used in the continuous spectrum. One final topic that I want to mention is what we mean by talking about functions of an operator. Really, we're interested in functions of observables. This is the main case in which it's used in quantum mechanics as a function of an observable. If A is any operator, there's certain functions that are trivial to define. I mean, for example, A squared is just equal to A times A. You can multiply operators, so that makes sense. In fact, any polynomial of the operator is also clearly defined because you multiply by scalars as well. But what about other functions such as the exponential of an operator or the log of an operator? Or how about 1 over A minus small a? These are possibilities here. Or how about a delta function of A minus A? These are things for which there's no Taylor series. A delta function has no Taylor series at all. What does that mean? You could have discontinuous functions. Can we define the function of an operator in more exotic cases like this? The answer is yes. Let's take the general. I'll use this notation I developed earlier for the resolution of the identity in the case of an operator A that has both a discrete and a continuous spectrum. And this is what it was. I'll remind you. It's the integral over d nu, I called it, of a nu r, outer product with nu r, like so. And we will define the function of the operator A to be the following. It's a sum on n and r, like this, A sub n, in r outer product nr, plus the integral d nu of A of nu, outer product nu r, like so. This is a definition of the function of an operator. Which
Do you
covers,
mean f of an?
so I mean what?
Do you mean f of an?
I think I mean a sum in here. Sum on R has to go in here. Do I mean which? I'm sorry. What's the question?
You're not applying the function to the right hand side.
I'm applying the. I'm not sure. I beg your pardon. Yep, you're quite right here. I'm going much too fast. Let's do it right. The second term is this. I made several mistakes there. It's an integral in nu like this, and then we have f of a sub nu. Like so. Yes, thank you very much. And then I've got the sum on R. And then I've got outer product nu r. Like so. Yes, thank you. I'm sorry about the mess here. Goes like this.
The first term as well. The function should apply to
And
the
this should be f
eigenvalue.
of an here too. Yes, thank you. Yes, thank you. No, I think it's finally correct. So the idea is that you go to the well, in the discrete spectrum anyway, the discrete part of the spectrum is quite clear. You just go to the eigenspace of the operator. And on that space, as I mentioned, the operator itself, the original operator is just a constant, it's just an. Well, that's just a C number. And on that space, then you replace that C number by the function of that C number. That's what you do. As far as the continuous spectrum is concerned, you have these outer products here that came from the resolution of the identity, and you just multiply again the eigenvalue of the function of the eigenvalue by you multiply the projectors or the outer products by the function of the eigenvalue corresponding to the given value of nu. By the way, a special case of this would be where the function is just the identity function. In that case, the operator A is given by a sum on n and r of a sub n times nr outer product nr, plus the continuous part, which I won't bother to write out. But you can see that what this is. This is just multiplying by a sub n for the given projector. In fact, this sum on r here is, this part here can be rewritten in another way. It's a sum on n of a sub n times the projector Pn onto the nth discrete eigenspace. That's another way of writing this. And in the case of the discrete spectrum, this term would be all you'd have. Now the continuous spectrum can't be written in projectors in the same way, but anyway, this shows you what happens in the discrete spectrum. Okay, that finishes what I want to say about the Hilbert space mathematics. And so let me pause here to ask if there's any questions before I go on.
Yeah, can you just remind us, or remind me rather, why we have two indices for the discrete spectrum and the continuous spectrum?
Because in the discrete spectrum, it's because the eigenfunction may be degenerate, and this R is an index that I use to, as I say, resolve the degeneracy.
That's right. Thank you.
So, for example, if there's a twofold degeneracy, then the R takes in the values 1 and 2. And you can have something similar in the continuous spectrum. For example, in the hydrogen atom, just giving the energy of the unbound state is not enough to give you the wave function. If I also specify the angular momentum values L and M, then that does uniquely specify it.
Got it. So R is
Okay.
for resolution of degeneracy.
Yeah, so that's right. It's for resolving the degeneracies. And in general, you need it. Any other questions? Yeah,
To
yes.
follow up on that question, for solving homework problems, should we always be taking into account degeneracies like this?
Well, I think in the homework problems I gave this week, I think the homework exercises tell you what to assume.
Okay.
I mean, if not, if there's some confusion, send me an email and I'll clarify it. I tried to be clear about what was going on there. Over time, it's evolved into that.
And do you say that the degeneracy index could be continuous in some cases?
Yeah, it's not so much a question of cases. It depends on your preference, because remember, a Hilbert space always possesses a discrete basis. And so if you want to introduce a discrete basis into those eigenspaces, to uniquely indicate vectors in that space, at least for the bound states, you can always do that. However, you may want to make the thing an eigenfunction of an operator, and if so, it may have a continuous spectrum. And this actually occurs. I mean, we'll see this in the Landau problem.
And if that happens, do the sums over R become integrals?
Yes, they become an integral over R. That's right. Okay. If there's no other questions, I want to move on to the next major topic, which is the measurement postulates of quantum mechanics. And it looks like I just have time to get started on that. What the measurement postulates do is they connect all this mathematical formalism with the physics. And to present these as postulates here is to, in effect, make kind of a feeble attempt at a pseudo-axiomatic presentation of quantum mechanics. I call it feeble and pseudo because it's nothing like what you do in mathematics with, with axiomatic structures, logical structures. It's nothing like that. But that's because physics can't be. There's nothing in physics that can be axiomatized. It isn't like that. Physics is not like that. On the other hand, by presenting a kind of a pseudo-axiomatic structure, it lays clear the logical foundations of the theory and shows what assumptions are being made and where you might change them if you wanted to. And that's really the purpose of doing this. So let me proceed then with now what I'll call the physical postulates of quantum mechanics. So the first postulate is this, and I'll write this out, is every physical system corresponds, I'll indicate that by an arrow, to a Hilbert space, which I'll denote by script D using the same notation I've talked about before. The second one is that every pure state I'll put in quotes because we haven't defined it yet, of the system corresponds to a ray, which is a subset of the Hilbert space. Now, I'm going to leave the notion of a pure state undefined for the time being because we're not ready to say what it is. So just bear with me. That means that there's going to be some vagueness in what I'm doing, but I think still there's an awful lot of information that's contained in presenting the postulates in this form. And later we'll come back and correct that and define what a pure state is. But in any case, a pure state corresponds to a ray. And let me remind you that a ray is a collection of vectors in the Hilbert space, which just differ from one another by a normalization and a phase. Another way of saying it is that a ray is a one-dimensional subspace of the Hilbert space. Now, I'm talking about states of a quantum system. I've mentioned this before. I'm talking about the states of a quantum system. In this case, a pure state. We often use the language in which we give a vector which is in the ray, and we call that the quote unquote the state. But the state is really not the vector. The state is the ray, and the vector is just what you'd call a representative element of a non-zero vector that's inside the ray. All right. In any case, with that understanding, that's what the state of the system is. The third statement is that the third postulate is that every measurement process that can be carried out on the system corresponds to an observable, which I'll indicate by the general notation A, which acts on the Hilbert space E. The fourth statement is that the outcomes of the measurement of A are the eigenvalues of A. When you make a measurement of an observable, you get its eigenvalues, either the discrete ones, A1, A2, and so on like this, the discrete ones, or they can be the continuous ones, A sub nu like this, where nu belongs to some interval, Like so, either the discrete or the continuous cases. The fifth postulate is that on making the measurement, the probability of measuring A is equal to A sub n is given by the state psi sandwiched around the projection operator Pn, like this, divided by psi psi. Now the psi here is a non-zero element of the ray. And it's any non-zero element of the ray. It won't matter what its phase or its normalization is. By dividing by this norm in the denominator is a way of saying that the normalization doesn't matter. And the fact that this is quadratic in psi, both in the numerator and the denominator, means the overall phase doesn't matter either. So the probability depends only on the ray and not on the representative vector of the ray that's chosen to make the measurement. As far as the P sub n is concerned, this is the projector onto the nth eigenspace corresponding to eigenvalue A sub n in the manner I've just explained. All right, so this is, let's call this phi A, 5A. This is the case for the discrete spectrum. For the continuous spectrum, the probability of measuring A0 is less than or equal to A is less than or equal to A1. We define an interval I, which is equal to A0, A1. This is given by psi sandwiched around the projector P sub I, psi, divided by psi, psi, where P sub I is a projector corresponding to that interval. That's sick. This is the measurement postulates. The sixth postulate is that after the measurement is carried out, the state of the system is changed, and that in the discrete case, psi is replaced by P sub n acting on psi. And in the continuous case, psi is replaced by P sub I of the interval acting on psi. This is sometimes called the collapse hypothesis here, the collapse hypothesis, because it states that the wave function is changed by the process of the measurement. Okay. Now, these are the measurement postulates, and there's several things I want to say about them, and we're running out of time. Let me just say a couple of things about them in a qualitative way, and then we'll be done. The first thing to say is that these postulates certainly don't look obvious, and they're not supposed to be obvious. In fact, they were derived after a rather tormented procedure of analysis and interpretation, attempts at interpreting the equations, of mathematical equations that emerged from the early years of quantum mechanics, some of it before Heisenberg and Schrödinger and some of it afterwards, but with a great deal of controversy. And in fact, some of the controversy remains today. And there are alternative interpretations and at least attempts at alternative interpretations other than the ones that I've given here. This is something you might call the orthodox interpretation, the most standard one that's used. So that's one thing to say. Second thing to say is that, what was my second thing to say? Oh yes, a very important point is that it's obvious from looking at these postulates that they're stated in statistical terms. The probabilities that are given in item number 5 here are obtained experimentally by running an experiment over and over again, repeating an experiment with identically prepared initial conditions, which give you different outcomes, and gathering the statistics about the outcomes. So if you're measuring the observable A, you're going to get statistics on the outcomes, and the probability of getting A equals AN is determined by making a large number of measurements and then just doing frequency counts. Similarly for a measurement on an interval. So quantum mechanics does not tell you what the outcome of an individual experiment will be. What it tells you is the statistics of the outcomes of repeated experiments across an ensemble of identically prepared systems. And so what this means is that the state of the system, this ray here, which is, as I say, gives you the pure state of the system, the state of the system is not describing the state of an individual realization of a system or an individual measurement. It's rather describing an ensemble of systems. It's characteristic of the ensemble. Now, in quantum mechanics, we use language, and we will in this course, all the time, where we say something like the wave function of the electron. But in actuality, the wave function does not describe the property of a single electron. It rather describes the property of an ensemble of systems, each of which contains an electron. And it gives us the statistics of the measurement that is made across the ensemble. Now, I think I'm running over time, so I'll stop there. But those are that's especially the second point is the most important point to make about these postulates, is that they are stated in statistical language and statistical language only. We'll be talking about the Stern-Gerlach apparatus in a little while, next lecture. And for example, one of the things these postulates are telling you is that when you run a silver atom through a Stern-Gerlach apparatus, you may know that it's going to either go up or it's going to go down. But neither quantum mechanics nor anything else in the universe can tell you which way it's going to go. That's not determined by quantum. All quantum mechanics does is it gives you the probabilities. Okay, so we'll say more about that in the next lecture. So that's all for tonight. Are there any questions?
I got a question about the assignment, if now is the moment.
The assignment, what?
Yeah, the assignment about the second problem.
Oh, you mean the homework problem?
Yeah, the homework.
Okay, I'd be
I don't
glad.
know.
I'd be glad to talk about that, but let's see first if there's any questions about the lecture.
I have a small question about the lecture
Yeah.
in the part of functions of an observable.
Yes.
Can you show again the formula you wrote? Because I think it's different from the one in the notes.
I better write it out because I made a lot of mistakes in writing it out. If I have f of a, it should be this. It should be the sum on n and r for the discrete spectrum of f of a n, then the outer product nr nr. And then for the continuous spectrum, it's an integral over nu, and it's a sum over r. And it's f of a of nu, and then it's nu r outer product nu r. Now, is that different from what's in the notes?
No, that's what's in the notes. But I think before you wrote like the sum somewhere else.
Yeah, I'm sorry. I think when I was writing that out, I made about 3 different mistakes in writing that. But this then agrees with the notes. This is correct. I mean, if you just look at it, you can see what's happening. Is you just want to replace the eigenvalue on its given eigenspace by the function of the eigenvalue. And that allows you to describe all kinds of crazy functions, you know, discontinuous ones, delta functions, anything you want. It's not restricted to power series or things that can be expanded as, polynomials or things like that. In those cases, it agrees with the obvious definition, however.
Okay, thank you.
Okay, any other questions?
Yes, I have one. So like when you're writing about the resolution of P, the momentum space, I think like on your notes somewhere you write the psi x is equivalent to the cat psi. Is that what you mean?
No, I'm translating from wave function language to Ket language in order to get the formulas in the neatest possible form. And I'm assuming that you're familiar with doing that from your first course in quantum mechanics.
Oh yeah. I just like you are not mean they are the same. You just mean like.
No, I don't mean they're the same. Actually, I think I mentioned this in the first lecture. There's a lot of literature out there in books where people sort of assume that ket psi means the same thing as psi of x. But that's not the point of view that we'll take in this course. I don't think it's the most useful point of view. Rather, I think one should regard ket vectors as belonging to, the state space of the system, which is an abstract vector space. That's how it appears in these postulates here. You see, it's just a Hilbert. So we didn't say what it was. It's not a space of wave functions. And then, in effect, to derive wave functions from that using the formalism of quantum mechanics. By the way, as long as I'm pointing out things about these postulates, I should also point out that these postulates never mention wave functions. So, people learn quantum mechanics and it starts with a wave function, but these don't. See, this starts with the Hilbert space.
Yeah,
Notice also another interesting fact is they don't mention H bar either. We'll see where H bar comes in a little later. All right, any other questions then about the lecture? These are good questions. I'm glad you're asking them. Are there any other questions about the lecture?
Yeah, just the first postulate here. If the physical system doesn't have a discrete spectrum and we end up having to deal with sort of these pseudo eigen functions that we talked about earlier that are like these plane waves, those don't belong to Hilbert space, do they? Or
No, they don't. No, they don't. But the physical states of the system do. And those things that don't belong to Hilbert space are not physical, so they actually don't live in the real world.
Okay, got
They,
it.
they live in theory. Okay. Now, one of the questions that these postulates lay open, and this is what we'll address next time, is for a given, like in a lab, you have a real physical situation. How do I know what the Hilbert space is? And so we'll give you we'll go through an example of that, so you can see how in effect, you can construct the Hilbert space out of the results of experiments. It's not something that's God-given somewhere. Okay, any other questions? All right, I think when yeah, so I think what I'm going to do is to stop screen share because I don't think we need it anymore. There was a question, however, about the homework. Can I take that question now?
Okay, well, it's about the second problem. Well, the first part about the 2A, that I could do it, but the 2B, I mean, I'm not well familiarized with deriving operators, and well, I like doing things like I got to an expression with two sums, and like well, I'm a bit stuck there, so I wanted to ask for a hint or indication.
I don't know if you can see me, but I'm actually flipping through my notes on this to find that problem. So I know what it says here. You can say it's problem 2, right?
2B, yeah.
2B here.
And well, I have the intuition that I have to use 2A,
2B.
but I don't exactly know where.
Yeah, so 2B is a harder problem, isn't it? So did you solve 2A?
Yeah.
And how did you do that?
2A, well, yeah. I followed the hint and found that deriving that function, I get to a differential equation, and like then I proved that. Sorry,
right.
and
yes, right.
And then I proved that the like the right term, including lambdas, satisfies the same equation with the same initial condition.
Okay, so I'm not prepared to explain part B to you because I haven't looked at it in more than a year.
Okay.
Except it requires some, you have to do some innovative thinking, and that technique that was used in part A is also useful in part B, or at least that's one of the ways of doing it. Okay. So well, I'm afraid I can't really help you much tonight.
Okay, well, if not, I can ask on.
If not, you can ask the TA, the GSI, I mean, or you can come to my office hours on Friday.
Okay, about that, well, on Friday we have the office hours, and also the we have to hand the homeworks. So
that's right.
I don't know if maybe it would be possible to change the office hours so we can ask you about the homework of that week. I don't know if
well, I kind of let the GSI take care of that, and then I have my office hours in the day that it's due. Actually, I found in my experience, if I have my office hours, one day before the homework is due, then nobody comes because they haven't started the homework yet. At least it seems that way. So my choice of the time for the office hours is based on, kind of over the years, I kind of optimize when I get the biggest turnout.
Okay.
Yeah. So anyway, you still have 5 hours after my office hours to, to write up the solutions.
Okay, then I will speak tomorrow with the GSI. And,
okay, great.
And I see. And just another thing, in the third problem, we are asked to find expressions for the coefficients for a matrix M.
Yeah, which
uh,
part is that?
3C.
Yes, yes,
And my question is if I can assume that I know the components of M, the elements of the matrix.
sure, because you're trying to expand it in the given basis.
Yeah, yes. Okay, then that's all.
Yep, okay,
Thank you very much.
all right, any other questions? All right, if there's no more questions, then I am going to stop screen sharing and we will be done for the evening. Let's see here.